let us start. Yeah, let me go through a couple of things which we discussed last week. So one is regarding properties of Laplace transform. Yes, differentiation in time. So yeah, there is still some confusion about this. So yeah, I will explain this more properly. Maybe last time I did not explain it as well as I would have liked. This is one, and the other thing is regarding these rules. Okay, so yeah, we went through most of these. Just one ROC which requires a minor justification. So yeah, this one. So conjugation in time domain is equivalent to conjugation in the Laplace domain, and yeah, S also you take complex conjugate of that, and yeah, why ROC stays as R if we take complex conjugates like this. Okay. So yes, it is almost straightforward. Just requires a bit of justification. So we had seen ROCs. They are yeah, either empty or the entire complex plane, or yeah, something like this, or yeah, parallel strips or left half planes like that. Okay, so five of those we had seen, and yes, we want to understand what happens when we take complex conjugate. Okay. Yeah. So if I take any complex number S, and if I take its complex conjugate, I reflect this number about the horizontal axis, right? Because we take the purely imaginary part and make it negative when we take complex conjugate. Okay. So all of these ROCs, if you can see, they are symmetric about the horizontal axis. Yeah? Whether it is the entire complex plane of right hand plane, left hand plane, or yeah, even something like this. Any question? Yeah, so it is symmetric about the horizontal axis. So yeah, when you take S star complex conjugate, the ROC, yeah, you get back the same ROC. Okay, had it been something like this, then ROC would change entirely. So complex conjugation due to symmetry of ROC region, yeah, you get the same R. Okay, so even though you are doing complex conjugation here, yeah, R does not. Okay, so that is one, and the other is as I was saying regarding this property. So why this quantity should be zero? Yeah, this is straightforward. Yeah, so let's try to go through this again. So e to the power minus st. So first of all, Laplace transform of xt and ddt of xt, both of them exist. Okay, so that is the underlying assumption, and with that assumption or hypothesis, we are trying to find the relation between yeah, the Laplace transform of x and ddt of x. Okay, so the Laplace transform integrals must converge both for dx by dt as well as for x. Okay, so this integral converges as well as the integral for x. Okay, so x times e to the power minus st with these limits also converge. Yeah. So when we expand this out, we got these two terms. Yeah, this is fine. So the exponential vanishes at one of the extremes depending on the sign of s. Yeah, and it goes to infinity at the other extreme. And since yeah, this integral exists, this quantity cannot go to infinity. So we said that at that extreme where this shoots off to infinity, xt must go to 0. Okay. And then there was a question that okay, so even if so, why the product should be 0? Why it cannot be some constant? Yeah, because we have 0 times infinity. So yeah, that could be anything in general. So we want to say that it cannot be a constant. I mean, it cannot be a non-zero constant. That this product has to be 0. and the explanation for that is as follows. Okay, so there we are going to use existence of Laplace transform of x. Okay, so we know that this exists minus infinity to infinity x, we not write e to the power minus x d. So this is strictly less than infinity by our hypothesis. So this product, this is over the entire real line. Okay, so at infinity, so one of the two infinities, we want to say that this cannot be a constant. Had it been a constant at infinity, one of the two, then this integral will not be finite. Okay, so if you integrate constant functions, the integral is not finite over unbounded interval. So if this approaches some constant at infinity, then this integral is going to diverge. Okay, so this product has to be 0 as t goes to infinity. Any non-zero constant, the Laplace transform of x is going to diverge.
So sir, it will be from converging, and when it reaches infinity, it converges to 0. If not, we will get infinity area.
Sorry, can you repeat? There is some disturbance.
Like sir, you are saying that when it reaches some constant when t tends to infinity, then the area diverges. Like the Laplace transform don't exist. Right.
Diverges. Area under the curve diverges.
But it is becoming constant only at infinity. So will it diverge?
So so yes, if you have functions which are becoming constant at infinity, the infinite integral is going to diverge, right? Because it is going to be infinite, forever. So yes, it becomes infinity as t goes to infinity. But yeah, so I mean, this is forever. It is becoming constant. Okay, so something which is a finite non-zero constant forever. You cannot integrate that over infinite interval.
Okay.
Convinced about that? That is as far as I can go regarding this explanation. Okay, so just convince yourself. Okay, your function is becoming a non-zero constant at infinity. Okay, so as t goes to infinity, the function is becoming constant. Then the area under that curve or function that cannot be finite unless it is zero. All right, so that is the argument why this product has to be zero. All right, so let's continue further. Okay, so these things we saw last time. So these are one-way implications. But note that the Laplace transform is not given. Okay, uh, only the ROC is given, and then you cannot go back. But if you are also given the expression for Laplace transform, then by uniqueness of Laplace transform you can go back. Okay. So ROC along with an expression of Laplace transform, then okay, you can use this arrow both ways. But if the expression for Laplace transform is not given, then okay, this is just a one-way implication. Here also we are not assuming any explicit expression in time domain. We are just assuming causality and stability, etc. But once we have explicit functions and yeah, their Laplace transforms, then okay, by uniqueness, this becomes both, and that is what we are going to see in this example. Okay, so now we are going to have a look at stability causality of the time domain functions. Okay, so let me recall this again. So causality implies that ROC must be right half plane, and the region of convergence must be to the right of the rightmost pole. Same holds for anti-causal signals or left-sided signals with yeah, instead of right, you just put left everywhere. For stability, ROC must include the j omega axis. Okay. So those are the ROC equivalents for these properties. Now we are going to use them to reconstruct time domain expressions and see what they are. Okay. So we are given the explicit expression for Laplace transform in terms of yeah, S variable. So this is a rational function, and the question is as follows: when the impulse response is stable and causal. Okay, and we are given these three regions. Okay, so now once the explicit expression is given, we know that there is a pole at -1, yeah, like this. There is a pole at +2, here it is, and there is a 0 at 1. Okay, so we know where our poles and zeros are. Yeah, and from Laplace transform pairs, we can also uh, guess what the time domain expressions are. We only don't know whether they will be right-sided or left-sided. Okay, so the inverse Laplace transforms for this, whether it is right-sided or left-sided, that will be determined by the type of ROC. Okay, so this corresponds to e to the power minus t. For example, this corresponds to e to the power 2t. So only thing is whether it is multiplied by u of t or u of minus t. That we need to figure out by looking at these ROCs. Okay, so let's look at this. We want this to be stable and causal. Okay, so is this ROC stable?
No.
This is not stable because j omega axis is not in here. Is it causal?
Yes, sir.
Yes, it is causal because ROC is to the right of the rightmost pole. Okay, so if this is our ROC, then we get causal HT, but it is not stable because this is not there. Okay, what about this then? Is this stable?
Yes, sir.
What about causality?
No.
Yeah, this is not causal because yeah, this is not to the right of the rightmost pole. So this is both sided. Okay, yeah, e to the power minus t is causal signal, so we will get e to the power minus t ut for this, but this is anti-causal. So e to the power 2t times u of minus t. That will be the time domain expression. So this is stable but not causal. What about this? Yeah, I've already written that here. This is anti-causal and unstable because j omega axis is not there, and anti-causal because yeah, everything is to the left of the leftmost pole. Okay. So this system is not both stable and causal. Yeah, for none of these ROCs it is both stable and causal. You can have causality here and you have stability here, but you don't have both. Okay. Yeah, this is an example of a stable and causal impulse response. So this is the Laplace transform, and if yeah, the ROC is of this kind, I'm sorry, this is wrong. It should be from -2, okay, not from -3. There is a mistake here, so please do that correction. ROC starts from -2. So this is right-sided and it includes j omega axis. So this is both stable and causal.
Sir, the implication that we derived earlier was only one-sided. So how can we say that if it is to the rightmost, then the reverse is not true, no?
Right. So that is when this implication is when the explicit expression for the Laplace transform is not given. Okay. Once the explicit expression is given, you know what is what does your time domain signal looks like. So here it can be either e to the power minus t ut or e to the power minus t u of minus t. Okay. So as long as the Laplace transform expression is not given, you cannot say, because yeah, we saw some examples where there are both sided signals for which you get your ROC to be the entire complex plane, etc. Okay. But those situations won't arise here because yeah, those signals, so let me open that. Yeah. So if you take signals of this kind, their Laplace transform involves yeah, these terms. So e to the power s square plus 4. Okay, so those kind of things will show up in the Laplace transform expression. Yeah. So once the Laplace transform expression is given, then yes, this becomes both sided due to uniqueness of Laplace transform. But if only the ROC is given, then this and here also we are not assuming any explicit form of the time domain signal. Yeah, we are just saying that it is causal or right sided. The explicit expression we don't know. So yes, qualitatively how the ROC will look like. Yeah. So if the signal is right sided or causal, this will be its ROC and etc. Once the explicit expression is given in yeah, either time domain or in the S domain, this becomes two-sided due to uniqueness of Laplace transform. Yeah, so I hope this is fine. This is causing confusion, then yeah, just think about this a bit. It's not a big issue anyway, just a minor point which we are discussing in detail. So ROC is also unique for each signal. But yeah, different signals can have the same ROC. So in that sense, yeah, there is no one-to-one correspondence between ROCs and the type of signal. But once you include the expression for Laplace transform along with ROC, then it becomes unique. Okay. So along with the Laplace transform and ROC, you have one-to-one correspondence between time domain quantities and yeah, S domain along with ROC. Let me see if there are any comments. Okay. So yeah, that is that. Okay, so we are more or less done with this discussion. There are some minor things which I want to mention. We will discuss them in detail later also when we look at systems. I'm just explaining these things in brief right now. So assume scalar transfer functions. You can have matrix transfer functions also, which we will see later. So this is a series combination. You can have a parallel. let me not. So this is straightforward. If you give an input here, yeah, you can see that y1 is so taking Laplace transform. Okay, in time domain it will be convolution. So x1 of s times g1 of s will give us whatever intermediate quantity we have here, and let's say y1 of s, and then y1 of s times g2 of s gives you y of s. Okay, so the effective transfer function is g1 times g2. This is straightforward thing. So for series or cascade interconnections of LTI systems, the equivalent transfer function is given by this, and yeah, here it is g1 plus g2. Straightforward thing. Okay. So there is one more kind which is feedback. We draw that here itself. So the adder is here. This is the input x. Call this g. Let's take this to be x. This is y. Alright. So yeah, this is getting subtracted. So let's call this here. Okay, so let's take transforms of everything. Okay, so that yeah, we can do things in straightforward manner, avoiding convolution, etc. Okay, so y of s comes in here. So this is called feedback. Okay, so yeah, before getting into this, let me also mention about open loop and closed loop. This is an example of an open loop system where there is no feedback. So whatever you give input, yeah, the system does whatever it is, whatever it wants to do, and gives you something back. So, open loop because okay, so the loop comes from here. So imagine a switch here. Okay, switch like this. And adder here. So with this switch open, y of s is just g of s times x of s. This is called open loop because this loop is open. Okay, feedback loop is open. And if the feedback loop is closed, then y of s is being fed back to the input. So input, whoever is giving an input knows what is the output, and then perhaps adjust the input appropriately. Okay, so that you get the desired output. So in open loop systems, yeah, the input provider has no idea what the output is. It knows, okay, there is a system here which does some function, and yeah, the input provider just feeds in the input without knowing what happens to the output, etc. So there may be disturbances, noise, etc. Okay, so in open loop systems, those things are not taken care of. we will not discuss those details right now. So, yes, sir. You can give many practical examples of both open loop and closed loop systems. Both are quite common. So when this loop is closed, what you get is the closed loop. Loop. So this is also called feedback, which we will come back to maybe in the last week or so. Okay. So now with this feedback, we want to determine what is the transfer function of this arrangement. Okay. So y of s is g of s times z of s. This is g times z. May not write s. But what is z? Z is h times y with a negative sign. Okay, so y times h is coming from here with a negative sign, and there is x coming in from there. Okay, so substituting for z, we can rewrite this like this. Now let's take terms in y to the one side. So y 1 plus gh coming in from this side. So gh times y, we are taking that to the left. On the right we have g times x. So y over x is g over 1 plus. For scalar transfer function. Okay. So single input, single output. So just one input and one output. In general, you can have multi inputs and multi outputs, and for that, for those kind of systems, you don't get scalars like this, but you have matrix transfer functions. We will come back to this later. For now, you can just stick to scalar transfer functions. Okay, so this is an expression. Badly drawn it. So y over x for systems with feedback of this kind. If h is unity, yeah, this is just, if this is just unit gain, then you get g over 1 plus g. Okay, so you will encounter these type of arrangements, and yeah, for the equivalent transfer function, you can use these rules now to find your equivalent transfer function. It's just like using rules for series parallel combinations of resistances. This is an additional rule we have. So, yeah, nothing too difficult or too deep about that. Okay, so that is one thing. The other thing is, yeah, the order of your transfer function. Okay, so order of transfer function or the system. So that depends on yeah, the degree of the denominator polynomial or the highest degree of the differential equation. So for example, if you have a differential equation of this kind, y dot plus ay is equal to x, say. Okay. Then the order of this system is 1, yeah, because this is the first order differential equation. If there are no derivatives involved, then yeah, this is a zero order system. Okay. If the order is 2 of this differential equation, then okay, it is a second order differential equation, and so on. Okay. So depending on the order of the differential equation, you will get appropriate powers in the transfer function also. Okay. Here g of s will be 1 over s plus k. And the degree of the denominator polynomial of this transfer function is 1. Okay, so this is a first order system. So you can be given either this expression or transfer function representation or impulse response, okay, whichever. You can always go to transfer function representation, no matter which expression you are given. And from that you can determine the order of the system. And there is also something called as realizing this system, okay. So what that means is the following. So in hardware, how you are going to realize this? Okay. So one way is as follows. You can design a hardware to realize this system as follows. So you can use integrators, by the way. Okay. Integrators are causal, but differentiators are not causal. Yeah. Differentiators can give rise to impulses, and if you write down the differential, the formula for differentiation, it takes into consideration the future values of. You can have left-sided derivatives also, which can also work, but yeah, the left limit and the right limit has to be same. Sorry, this is not minus. This is minus, not plus. Minus f of x. And in the denominator, whatever. Okay. So we want to avoid differentiators in our realization. Integrators are fine. Okay. So let's realize this using integrators. So transfer function for integrator is 1 over s. So you can write 1 over s here, or you can write this symbol also. Suppose we have y dot in here, and integral of y dot is y. Okay, and then y dot is equal to a times y, and that is a times y we want to subtract from the input. So this is our input. In the feedback, you are going to have a here, and that you are going to subtract. So this is like a hardware schematic of realizing your transfer function using integrators, adders, and multipliers. Okay. So we will always assume that our transfer functions are proper. Okay. So by proper I mean the numerator degree is less than or equal to the denominator degree. If it is higher, then you are going to have impulses and non-causal systems. We are not going to consider such kind of system. Yeah. So degree of this numerator polynomial is less than or equal to this denominator polynomial. That is always the underlying assumption. So this is the realization of the first order system. You can also similarly realize second order systems also. Okay, just requires a little bit of work apart from this.
Sir, could you please explain what is the relation between order and transfer function once more?
Yeah. So order, order is the degree of the denominator polynomial. In transfer function representation, order is the same as degree of ds. And in so this is in transfer function representation. In differential equation representation, it is the highest degree of your differential equation. So in physical sense, yes, these are the minimum number of variables which are required to describe or model your system. Okay. Does that make sense? Minimum number of variables. You can introduce redundant variables also, but we don't want any redundancy. We want minimum number of variables to describe our system. Okay, so if you drop any variable, then yeah, you cannot model this system with lesser number of variables. That is what is physical meaning of the order. Yeah. Does that make sense?
Yes, sir. Yes. Thank you.
Any any other questions? Okay, so one more thing is as follows. One more thing to notice. Okay? So rational functions are realizable. So you, in other words, you can build a system in practice, a real life system which has a rational transfer function. So we had seen examples of non-rational transfer functions. Yeah, this one for example. So signals of this kind. Okay, so okay, mathematically it makes sense to, excuse me, have this kind of quantities, but physically you cannot build a system which has this transfer function. Okay, this is not a rational transfer function, so yeah, that is consistent with that. So we only that's why we stick with transfer functions of this kind, okay, because they are realizable in practice. So this is a fact. I don't know if it can be proved mathematically or it is an empirical fact. Okay, so you guys can also have a look at this if you are interested, and let us know if you find anything on that. So yeah, I have not seen any mathematical justification. I have not searched for it also. I read it somewhere that okay, only rational functions are realizable, but I don't remember now where I read this. Yeah, we are taking this for a fact. Yeah, if you have any comments on this, then you can put them in chat box, or later on also you can include them. Okay? So it is unknown to me whether this is an empirical fact or it can be proved in theory also. So that's why all transfer functions which we will encounter, they are of this kind, rational functions. So yes, taking inverse Laplace transform, we are always going to encounter some manifestations of complex exponentials and yeah, so forth. All right, so that is that. Okay, so let us look at one more thing. Let's look at realization of this, for example, s plus 1 over s plus 2. So s plus a we saw, right? Yeah. So let's take a to be equal to 2. And this, now we can write as a cascade of 1 over s plus 2. So again, this is just one realization, and it is, I think, there in Oppenheim. There are multiple ways to realize this. So yes, you can have a look at them. This is not a very difficult concept, so I will not spend a lot of time on this. So this we had already realized here. And now, yeah, we want to incorporate this term also. Okay. So output of this is, yeah, as we have seen, this is y of s. And now, yes, we have s plus 1 times y. So s times y of s is equivalent to taking derivative of y. But we don't want to take any derivatives of y. Yeah, because we don't want any differentiators in our realization. And there is 2 times y also. So there is no problem. We can put a multiplier 2 here, that which multiplies y by 2. But we have y dot in here in this realization. Okay, so we can take y dot from this side and add that up with 2 times y. Okay, to get a realization for this cascade. Okay, so I hope that is fine. Y dot is already available in this realization. You just take it out, multiply y with 2 and add it up. So that's how you are realizing y dot plus 2 times y to the right of this. So that's how you can, that is one way to realize rational function. And any general rational function, you can write that down as a cascade of this degree 1 rational function. So just put all of them in cascade and get a realization. Okay. So I hope that is fine. Okay, so there is one more thing. So yeah, for second order system, yes, you have this polynomial of second type or second degree. B2BS maybe, or BS, whatever. I forgot what do we write here. I think it is just B, not B. Okay, so this polynomial can have real roots, real distinct, real repeated, complex. Yeah, let me not write all that. You know that, right? So roots can be real or complex, first of all. So real and complex. Those are the two types, real and complex. So real can be repeated or they can be distinct. There are just two roots. Complex can be purely imaginary or with non-zero real part, and you can have positive real part or negative real part, etc. Okay, so these coefficients are real. So the complex roots are always going to be complex conjugates. Yeah. And based on that, yeah, there are various things. Okay, so yeah, all kinds of those things show up in these kind of systems. These are called second order systems, and yeah, depending on those roots, you have damped system, undamped, underdamped, overdamped, etc. So maybe later I can just refer you to one of the Oppenheim's slide or whatever. Maybe right now I can do that. So just have a look. That is not a very deep conceptual discussion anyway. I think it is in the link. Okay, I don't remember now. Let me see if I can figure it out quickly. Yeah, second order. Okay. Yeah, so you have all these types, okay? Instead of Bs plus C, you can write it like this, okay? Omega n theta, and then depending on these values of theta and omega n, yeah, you can have complex roots or real roots, etc. And yes, this I leave it to you guys, okay? This is not very deep, straightforward. High school arithmetic basically. So maybe we can have a look at these things later on if we have time. So just go through this. Yeah, I'm already running out of time. So I wanted to quickly do Z transform also today. At least give you a brief about Z transform. I don't think I'll be able to do that. But let us see. let's do this nice thing. Laplace versus Fourier. We have had a look at both Laplace and Fourier transform, and let's do this matchup. Who wins? Laplace wins or Fourier wins? Okay. So this is our geeky matchup to the I don't know, the famous battles, whatever, Tiger versus Lion or Kong versus Godzilla, whatever, Batman versus Superman. So yes, Ford versus Ferrari. Okay, so let us see who is better, Laplace or Fourier. Too bad we don't have a poll here. Otherwise, yes, we could have taken a poll who wins. So Laplace says that okay, Laplace is more general than Fourier because all Fourier can do, Laplace says I can do, but I can do better. Laplace can handle ramp signals or parabolic signals which cannot be handled by Fourier because these are unbounded and Fourier integral diverges because the signals themselves diverge. But these do appear in practice, okay? In electrical or other systems, you will encounter these kind of signals. So Fourier gives up, cannot do anything. But Laplace with his ROC, he gives transforms, and you can still go to frequency domain and do things. Okay. So that is there is one point there for Laplace. But Laplace also distorts things. Okay. So Fourier keeps distances as they are, so it does not change quantities, does not change inner products. It has nice orthogonal properties, but Laplace distorts things and crams up things, etc. Okay, so there is a certain advantage, but it comes with a cost. Okay, so 1-1. So Laplace, Laplace can handle all kinds of these systems. Okay, so in our first year's course, we had seen DC circuits, both resistive and with capacitors and inductors also. So with capacitors and inductors and with switching involved, we stick to time domain analysis. Okay, for AC, we went to phasor domains and turned all differentiation into multiplication, etc. But we did not have that luxury in DC. Yeah, we had to solve differential equations because Fourier does not help. If there are switches or if you have constant DC signals, then but now with Laplace, you can handle those switching circuits. So you can, I think those who are taking electrical networks must have already seen such examples, but take some electrical circuit with switches, etc., and just solve them by applying Laplace transforms. Okay. All right. So just do that exercise to see that you really understand Laplace transforms. And now whether you are in DC, AC, it does not matter. You can just apply Laplace transforms and solve this algebraically rather than solving differential equations. Okay, so that is one exercise you can do. Okay, so second point for Laplace is stability. So Fourier cannot say anything about stability. You have to go to time domain and see if the function is absolutely integrable. But Laplace gives us interpretation in terms of poles. Okay, so if you know if your system is causal, etc., then just by locating poles of the transfer function, you can conclude about stability. And, Laplace has another advantage. Okay, so that's when Laplace thinks like he has got Fourier and there is nothing Fourier can do now, but that's when Fourier comes up with his FFT and Laplace is left in the dust and Fourier wins hands down. Okay, So that's my version. Laplace fans can cook up Laplace's version. I'm a fan of both Laplace and Fourier, but I like Fourier more. So, yeah, in my version of this battle, Fourier wins. So you can spice it up and you can make Laplace win. Okay. So that was our special Diwali battle. Okay, so let's quickly see at least the definition of Z transform. I'm not going to go through too many things regarding Z transform because we had discussed Laplace in detail, and this is just straightforward generalization. But yes, if you have any questions, then we can always discuss. Okay, so I'm going to give some briefs, and yeah, you can refer to books, and yeah, it should be straightforward. Okay. All right. So let's start with the definition first. This is the Z transform definition. So xn and z to the power minus n. So if you imagine, if you recall your Fourier discrete time Fourier transform, you had x of n and this complex exponential in here. Okay. So let's try to understand Z transform by recalling our DTFT. So Z is a complex number, and let's substitute a polar representation for this complex number. Okay, so Z is r times e to the power j omega. So r to the power minus n we are consuming with x of n, and now this is just the DTFT of this signal, and yeah, just what we did in Laplace and its inverse Laplace. Inverse DTFT gives us inverse Z transform. This 2 pi integral that we can identify with a unit circle. Okay, so whether we have this 0 to 2 pi, or we are integrating over omega varying from 0 to 2 pi. These are the same. So this 2 pi integral, we can write it as a closed loop integral. Yeah, this is this circle is our closed loop. We are expressing this integral over this closed loop. Alright, and just as we saw in Laplace transform, there is going to be a region of convergence in Z transform also. Okay, so region of convergence is precisely the region in the Z plane where this integral converges. Okay, in Laplace transform we had these half planes, and in Z transform we are going to get circular regions. Okay, let us understand why that is so. So this x times n and r to the power minus n. Yeah, this we want this to converge. So r we want to choose appropriately so that this integral converges. So for example, if our signal is of this kind, a to the power n times u of n. So let's take a causal signal. And if we take its Z transform, so this is x of n. Let me not write n here. So x of z is start from 0, so 0 to infinity, a to the power n, z to the power minus n. Okay. So values are identically 0 for n negative. That's why this summation. And now this sum we can write that as a times z inverse raised to the power n. Okay. Now, yeah, for Z transforms and their inverses, you need to know this power series. So 1 plus x squared, etc. up to infinity. That is equal to 1 over 1 minus x, provided one condition. Modulus of x must be strictly less than 1. Okay, so this converges provided mod x is strictly less than 1. Okay. So we want mod of this to be strictly less than 1. So mod of a over z is strictly less than 1 for this sum to converge. So this is our ROC, and let's write down this power series in terms of this expression. So this is 1 over 1 minus az inverse. Okay, so this is the Z transform. And this is the ROC. So let's sketch this ROC. Mod A we want to be less than mod Z. Okay, so in other words, mod Z should be strictly bigger than mod A. So mod Z is just R because mod of e to the power j omega is 1. So ROC looks like this. So this is your circle of modulus A, mod A. And ROC looks like this. Everything outside this. So that is for right-sided signals. Okay, if you get left-sided signals, just check this. Okay, in that case, this will get reversed, and what you get is everything inside the unit circle. For both sided, you get strips like this annular region between the two circles. So again, there will be 5 types of ROCs. All 5 are here. Complex, complex, entire complex plane, empty, outside the circular disk, inside the circular disk, or in between the two disks. Okay, and all other properties. So stability, etc. These also you can translate. Go back here. Okay, so causality will give you ROC, which is of this kind. Okay, everything outside of the pole of highest magnitude. Okay. For anti-causal, will give you everything inside to the pole of the least magnitude. For stability, here we had j omega axis for stability, and it turns out that we will have a unit disk. Why is that? Because yes, if you go to definition of the Z transform here, yes. So if you substitute R is equal, magnitude R is equal to 1, then you just get DTFT. Okay. So for DTFT to exist, the unit circle must belong to ROC. Okay. So that is the equivalent condition for stability of discrete signals. Okay. ROC must include the unit circle. Okay, so that was a very quick view of Z transforms. This is also there. So realizations, yes, you can do realizations using delays instead of integrators. So here we use operators, and in place of that you just put delays. Okay. And using delays, adders, and multipliers, you can realize rational functions in discrete domain. I mean the Z transform. And this initial or final value, this final value theorem. Okay. So yes, for final value theorem to hold, you must have the unit circle in the ROC, because we are taking this limit. Okay. So it will not hold when the unit circle does not belong to ROC, and just go through this straightforward manipulation. It almost comes out for free. The remaining properties are just go back to Laplace transform and DTFT. Everything about Z transform just follows from that. There is a unilateral Z transform also, which is analog of unilateral Laplace transforms, which takes care of initial conditions while solving difference equations. And there are all these natural analogs. Okay, if we have time later, yes, we can discuss a few more examples. But yes, you guys can have a look at these things from Oppenheim's book or whichever book you are referring to. With the understanding of Laplace transform and Fourier transform, yes, you should be able to understand this. Okay. And just have a look at this order things also. Okay. So this is also something which is I'm not going into much of details because yes, this is not that complicated and sort of boring, and you don't want to hear it from me with my boring monotonous voice. You can just read it rather than me reading it for you. Okay, so I have overshot a bit, so sorry for that. I will stop with that, and happy Diwali to all. And tomorrow we have a holiday, so we will meet on Friday. So, thank you all for attending.